We'll be having Ricardo's second lecture on transseries and resurgent.
Okay, so let me just quickly remind you where we stopped last time, and then we'll take it from there. So we wanted to compute the partition function, time model partition function, which looked like this. Just a one-dimensional integral. For a quarting potential. And we already discussed that we're using the variable x is h bar lambda. And then we saw that it satisfied the differential equation, second order differential equation. And we solved this equation using the methods of transseries that we had been discussing earlier. And so basically there was a Z0, which was given by an asymptotic series. Let me not write again all the details of that asymptotic series. And then there was another solution with the exponential guy in front. Alright, everybody remembers this? Now, the point was we were computing Borel transforms of these guys. So we're computing Borel transforms of this guy. Well, yes, Borel transforms of this guy is a series. And we were about to discuss what was the resulting structure. And the structure was the following. So we first computed the Borel of phi 0 next to its singularity. Remember the singularity was at plus 3/2, the instant on action. And we find that there was a number, which was in this case plus 2 times stuff. And when we were computing the Borel of phi 1, we found that there was another number times similar stuff. And the number now is -1. Yes. And the stuff was kind of universal. So there was, in both cases, there's a pole. In this case, at plus instant on action. In this case, the pole was at at minus instant on action. In this case, the pole was at plus instant on action. And then what else was there? Which was universal was the logarithm, a logarithmic branch cut. In this case, also a logarithmic branch cut at the other singularity. And then there was holomorphic stuff we don't care about because we're just looking at the singular structure. Right? And what was in front of these people? In this case, it was just Z01. That was just the number, the first guy here in this power series. And here, Z00. Right? And then in front of the log, there was another Borel. And the Borel was evaluated in a place where it is regular. So in this case, the Borel, let me put it here small, S here, S minus A, and the Borel was the Borel, in this case, phi 0, in this case, phi. Okay, so that's where we stopped last time. And now what I was saying is that the structure of singularities is universal. And so I want to try to abstract to the point that I don't care about all that's universal. And what's universal, let me actually change it to colors. What's universal is everything which is not in white. Right? So now, I know that at the singularities of phi 0, I find the resurgence of phi 1 up to the Stokes constant. Notice that the Z0 is just part of the phi 1. It's just the constant term. The constant term needs to be handled separately because if you recall, the Borel transform would be singular for a constant term. So that's just a detail. I don't even care so much about that guy. And at the singularity of phi 1, I find the resurgence of phi 0 up to a Stokes constant. And where am I evaluating these guys? I'm evaluating this guy at S, the Borel variable. Here A, and here S, goes to minus A. So how can I abstract and just look at the white stuff? It's very simple. Basically what I'm going to do is I'm going to define an operator. We had already seen what that operator, well, not was, but it appeared before. And I'm going to define it in this way. Alright. So if you recall Borel plane that we had discussed last time, there was possible singular directions, theta. There was a singularity there. And to avoid the singularity, we discussed that we could go right above it, and I call that the resummation above the singularity, or right below it, and I call that F theta minus. So basically what this alien derivative, remember that was the name of the object, what the alien derivative is doing is an average. It's averaging above and below the singularity that I found on the Borel. And besides the averaging, I have an exponential in front. And the reason why I have an exponential in front is just to kill the exponential that comes from the resummation. If you recall, the resummation is a Laplace integral, and so it's got an exponential in the integral. And if I use this definition, then it's quite simple to see that all those expressions get much simpler. So basically all I get is that from the first one on phi 0, what could I have? I can act with delta. Now delta will only be non-trivial if I'm at the singularity, because anywhere else there's no singularities, and so that means the F theta plus is going to be equal to S theta minus. So it's going to be 0 everywhere except at A. And what is it going to be equal to? Well, the minus 2 factors out. I'm sorry, the plus 2. The plus 2 factors out. And what's left is the difference between those resummations, which is going to be the phi 1, up to an exponential, which is killed by this exponential term there. So basically all you got is this. And if you do the exact same calculation for phi 1, it can only be 0 where there's a singularity. And it's going to be basically that. So that's it. These two formulas basically encode all the complexity of singularities on the Borel. And the good thing about this alien derivative is that it satisfies Leibniz rule. Here it's an integral way, because basically if you keep iterating, you just get zeros. But in generically, it is a derivative. It satisfies the Leibniz rule. Alright. And so, last time we were discussing how can I encode everything into this Stokes automorphism. You should tell me how can I go around all the Borel plane, and it was this object that I wrote like that, and it's basically the exponential of the sums of the alien derivatives. And now, let's make a couple of calculations using the formula we have. So this, if you recall, was the exponential of a sum over singularities. Now basically, I have only one singularity along theta equals 0. That's that one. And one singularity along theta equals pi. That's this other one. There's nobody else, so this sum is going to collapse at some And let's just use this formula and see what we can get out so that we get some intuition for what it's telling us. So it's, again, I either have, let me also draw maybe the Borel point here, down here. For this particular case, so basically I have one singularity here at s equals a, and I've got a singularity here at s equals minus a, and this of course is theta equals 0, and this of course is theta equals pi. So now let's see what that object will do. So if I act with the Stokes along 0, and it's an exponential of alien derivatives, and the only non-vanishing alien derivative is the one that acts on phi 0, I can only have this operator acting on phi 0, nothing else. And what it's going to be, it's going to be the exponential of minus a over x times delta at plus a. There's nobody else, there's only one singularity. And if this acts on phi 0, it's not very hard to see that the exponential is going to truncate. So there's first term in the exponential is a 1, so this is phi 0. The next term in the exponential is the linear term, and delta plus the phi 0 I've already computed, and it gives me plus 2, well, minus 2. Did I switch a sign here?
Minus on the exponent.
Oh, yeah, that's right. Minus 2, exponential of minus 3 over 2x by 1. And then the next guy would be the second derivative, which is 0, because delta plus a acting on phi 1 is just not going to work. And the same thing happens if I do it along pi. If I do it along pi, I have the exponential of plus a over x delta of minus a. It can only act on phi 1, because that's the only singularity that I have there. The linear, the 1 gives phi 1 back, and then the rest is going to give us plus exponential 3 over 2x phi 0. Okay? And you say that's not particularly illuminating, but it's just a standard application of this formula. I agree, so far it's not particularly illuminating, but let's wait for the next two formulas where they make things complete. So now, this is the way the Stokes automorphism is acting on the asymptotic power series. So if you remember, the transseries was sigma 0, transseries parameter times z0 plus sigma 1 times z1, right? And z1 in particular has an exponential inside it. Exponential of minus 3 over 2x times the sum, well, which is times phi 1. Right? So I need to take those things into account. So the next step will be to do the calculation for the components of the transseries. And let me just write the results. This, again, all these calculations are elementary. The action on z0 is basically the same as acting on phi 0, except now I can put the exponential together with this guy to get z1. So I'm going to have z0 minus 2 z1, and if I do the same along pi on z1, basically I have to put an exponential back in that comes with this one to give me z1, and which kills this one to give me z0. So this is basically z1 plus z0. And you say, okay, that sounds, or at least looks a little bit better. So the final thing I should do is to use this formula to see how it acts on the full transseries. And when it acts on the full transseries, we'll see that this basically incorporates Stokes phenomenon. We can already have a feeling that something is going on because there's some shifts that must be associated to the transseries parameters. And it will have the monotony of the full solution. So the result that we're finally going to have is the obvious one. We're going to have that S0 plus is equal on the transseries, and let me put everybody together. I have x, I have sigma 0, I have sigma 1. So I'm comparing what's going on here. The difference between this guy, S0 plus, and this guy, S0 minus, right? And you remember from last time that the difference was given precisely by that operator that we already computed. So now I can compute this difference. So the difference, which is there in pink, translates to this formula. Okay? So the x, of course, doesn't change. Here what we have, the sigma 0 isn't changed, but the sigma 1 jumps. So this is an instance of Stokes phenomenon. The sigma 1 is jumping to sigma 1 minus 2 sigma 0, and the minus 2 is the Stokes constant. Right? And the reason why it's jumping is just because of the formula above. And I can write exactly the same at pi. So I can do this comparison instead. This one minus this one. So that being ds pi plus, that's minus. And so z. You just read it from the second formula. And what you get is that now the jump occurs in the sigma 1. I'm sorry, the sigma 0. The jump is given by sigma 1. So basically now it's sigma 1, which is unchanged, and the jump is occurring at the level of sigma 0 by just sigma 1. Sigma 0 jumps to sigma 0 to sigma 1. And in particular, I can define a monotony operator, which is basically given by sigma pi after Stokes pi after Stokes 0. It tells me what happens as I go around the Borel plane. That's what this monotony is doing. And if you compute it, you get the result that should be sort of familiar, which is basically that monotony. We need to go 4 times around the origin, find the identity. So you see that once I know the alien algebra up there, everything else follows. But you know, this is high school algebra. It's really a triviality once you write it in the correct language.
So is this obvious? If this sigma pi and sigma 0 to the power 4
This, if it's obvious, I think it's obvious by just elementary algebra, which is you just do the calculation around. If you're not happy and you want to see a plot, you can make, I have a plot here, but I don't have a projector. You can see a plot that if you start following the transseries and you plot it against the vessel, because it's just a modified vessel after you peel off an intervention, you see that you really have to go 4 times around so that the loop of the vessel will close upon itself. I'm not trying to draw it on the blackboard, but I think the idea is clear.
Does this 4 have a physical meaning?
Second.
Does this number 4 have a physical meaning?
It's just a monotony. It's how many times you need to go around and come back to the same place for the vessel function. If you do this for the area function, you get 3. If I'm not mistaken, if you do this to the function, you get a monotony. And in particular, if you look at nonlinear problems, then the monotony gets much more complicated because you can get even Riemann surfaces which are infinitely sheeted.
This is something that you have to compute by doing all these things. It's not simply related to the original model. Some parameter. Not related to some parameter of the original model that you have studied.
No, this is just a property of the solution. And in fact, if you remember, this is a property of all solutions because I haven't specified sigma 0, sigma 1. So right now I'm still considering the general solution to my differential equation. And general solutions to this differential equation have this property.
To do all these things, you needed to actually be able to solve the full problem.
So I didn't need to use resurgence anywhere to solve this because it's a vessel function. Again, all I'm doing is finding the simplest possible case where you're familiar with the results to show you that you can get results you've already seen probably with high school algebra, plus minus. As long as you know that structure of everything. Right. Now I can show you that this generalizes almost everything I said for a linear problem, which is a time model, which is as simple as you get, works the same way, no matter how complicated your nonlinear problems can be. Alright, so let me say a few words about that. No, I'm sorry, let me say one thing before because it's probably going to be important at the workshop. It's the following. No, actually, I can also get some extra mileage out of these concerning asymptotics. So, last time I was also telling you that there was this relation between perturbative data and non-perturbative data, and let me make that also explicit here. So now, what's perturbative is phi 0 and what's non-perturbative is phi 1. And last time I was telling you that if I know phi 0, then there would be phi 1, phi 2, maybe I'm not sure what the notation was, that phi 3, and so on. And so all these instantons could predict the growth of the phi 0 set, right? Let's make this a little bit, and you could decode, but I don't want to do the decoding right now. You could also decode non-perturbative content out of the perturbative data. So now I'm going to consider this case, our example. There is no phi 2, there is no phi 3, there's just a phi 0 and a phi 1, and let's find what this relation between perturbative and non-perturbative data looks like. And this is actually an old story. This is late 70s, early 80s, that you can write down basically the Cauchy theorem. And the Cauchy theorem can be written as a dispersion relation. It's not too hard to see that if I am on the x complex plane and I have some cut, wherever it is, but I do not care about it, then it's easy to write any function. No, I'm not thinking about anything special. It's just given by minus 1 over 2 pi I times the integration along the ray of the cut. That's just theta of the discontinuity of the function around theta. W minus x, right? This is just a simple dispersion relation that you can write down out of the Cauchy theorem, second year complex reference, whatever. So again, very simple formula. But now we can try to apply, and this has nothing to do with resurgence, it's just a formula in complex analysis. We can try to use what we know from the resurgent structure to get some mileage out of this. In particular, what can I write? I can write the following. Two relations. The first was what I already wrote here, that f theta plus is f theta minus after applying the Stokes automorphism. But I can define the discontinuity of my power series along this, by the way, directions where I find singularities are known as Stokes directions. Again, basically everything is Stokes something. So along this Stokes line, I have a discontinuity because I can write this equation basically as a definition as s theta plus minus f theta minus is equal to minus the right summation of the discontinuity along theta, right? That's just a natural definition of the discontinuity. It's the difference between resumming on one side and resumming on the other. And now I'm just making a trivial statement, which is that the match of these two equations tells me that the discontinuity is given by the identity minus the Stokes automorphism. And for all our power series, I know how to compute the Stokes automorphism. So if I know how to compute all those Stokes automorphisms, I know how to compute all these discontinuities. That's just by definition. And then if I plug them here, I can try to get something out of this equation. And what this equation is going to be is basically a large order relation. Let's see what I get. I just apply that using the results which are here on the blackboard. And let's erase this side and see what the calculation tells me. And the calculation is very simple because all I have to do is basically translate where F was. I am now going to use the asymptotic series of the perturbative sector. Alright? And so this should be equal to minus 1 over 2 pi I. The integration along the discontinuity, and I know how to compute the discontinuity by using the results here. Right? In fact, it's not hard to see that discontinuity is proportional to an exponential times phi 1. So basically what I'm getting on this side is going to be the integration from 0 to plus infinity of 2, the Stokes constant is appearing, divided by w minus x, times the exponential, that's that exponential, minus 0 to x, times phi 1. Phi 1 is just the power series. I'm sorry, it's not x here, it's the other, because it's a function of W extent. And the power series is that k1 wk. I haven't done anything, except that now I can just look at what this implies. I have the equality of the power series, I can see what it implies for the coefficients. And this just says that, let me write this explicitly. This is going to be minus 2 over 2 pi I. I'm putting 2 over 2 pi I to see explicitly the Stokes constant appearing, and minus 1 factorial divided by 8 n. And then I have z01 plus a divided by n minus 1 z1 plus a squared 1 and so on. Alright? So here is a materialization of the arrows that are in the blackboard above. What do we see? We see that the large order grows of the perturbative coefficients at leading order grows as n factorial, and that subleading has the exponential contribution that comes from the instant on action. We had already seen this last time as an expectation. There is an overall factor which is appearing here, which is the Stokes constant. We had already also discussed that last time, that these were the hard numbers to compute. Although the structure of this large order relation is universal, explicitly saying what the Stokes constant will depend on each problem that you're studying, and you have to compute it, it's not easy. And then I see that at leading order I have the tree level, if you want, or one loop, depending on how you want to count the zeros and the ones. Usually it's one loop, one instant on contribution, 2 loops, 3 loops. These guys get suppressed in 1 over n, the 2 loops. The 3 loops get suppressed in 1 over n squared, and so on and so on. And if you were to have a nonlinear problem, so if orange stuff, which is up there, existed, then I would get here, I would have summations of stuff that would go as just schematically 2a to the nth power, blah, blah, blah. 3a to the nth power, blah, 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 and so on. So not only would I have power suppressed corrections to the leading asymptotics, I would also have exponentially suppressed corrections to the leading asymptotics. And so this is how, the more non-perturbative data I have here, the more I can say how the large order growth of the perturbative guys are going to go. And the more I have, the less I'm saying about the large order, and the more I'm saying about the exact perturbative guys. And if, on the other hand, I have the perturbative coefficients, and I know how to decompose all these numbers into their 1 over n components and 2 to the minus n, 3 to the minus n, and so on components, I'm also extracting all the non-perturbative information directly out of the perturbative coefficients.
How this is working? So what you have to start with, that you can do some perturbative computation for some quantity in some perturbative area.
Yes.
You have these numbers z and zeros.
Yes.
So these are the numbers that you can compute up to some order.
Yes.
10, 15, 20 or whatever.
Yes.
Okay. Now, so let's say I have 10 of them.
Yeah.
Okay. And then what you are claiming that you can find out, these, so let's say there are more incident factors, which I don't know. How many incident factors are there? This will be determined by finding out the.
So the way you would do that is, I have all my perturbative data. I mean, I'll show you some plots at the workshop. I have my perturbative data, and I'm going to plot ratios of the perturbative data. So let me plot here. Do I have any ratio here? Yeah. Let me try to make here a drawing. Yeah, right here. I don't have to make a drawing. Let's imagine that I have data, which are basically the Z and series. Okay? And let me multiply this by 2 pi A n divided by gamma n. So I'm multiplying basically by universal growth of n factorial and subleading instantaneous. And then I'm going to plot this.
You already know.
I can also find it out numerically. I'm just going to give you one example because I have the plot here and I can draw it for you. But I can also tell you how to get instantaneous. Hang on a second. And I'm going to plot these guys against n. And if you do the calculation, you put it in the computer. So you say that I have, I don't know, let's see, how many I have 200. I have computed 200 of these guys. So I can go up to 200. And I start plotting this sequence. I'm plotting this sequence. And what I'm going to see is that they behave like this. Are the dots clear? Actually, I've drawn them bigger. So they're behaving basically like this. So this means that at large order, they're being asymptotically approaching the result that I'm expecting to have, which in this case is basically dictated by this guy. All right? And this is square root of 2, essentially. So by plotting a sequence of data that I have managed to compute, I can find out what's that action. So I'm extracting out of perturbative data, numerically, a result about what the one loop, one instanton gas should be, without having to compute it directly. So then I can be starting smart and trying to compute ratios of all these perturbative guys to try to find, I could have done something else before. You were complaining, instanton action. Yeah, I could have plotted the ratio of, say, Zn divided by Zn plus 1 times n or divided by n, whatever, this thing which is the factorial. And then that's going to be A. And then you plot that sequence, and that sequence must asymptote to A. And then you can, remove Z01. Now that I have computed it, I remove it from this sequence, from the yellow sequence, I remove the blue contribution, and now I'm going to try to zoom in into the 1 loop, or 2 loops, 3 loops, 4 loops. And then, harder, I can imagine, wait, now I want to find out about 2 instantons. Then I have to remove all these series, for which I also only have finite amount of knowledge. But I can do a numerical approximation to the Borel resummation of that series, which is known as Borel-Padé, where I approximate the Borel function by some rational function so that I can have some hints of where their similarities are going to be. I resum it, I remove it, and I start looking at the 2 instanton, and then the 3 instanton, and so on. I'll show you some numerical plots at the workshop.
Just much more my question. Let's do some counting of equations. How many equations you have and how many things you want to determine out of these ones?
Oh, but look, I mean, as I said, if you only have finite data, you only have finite many things you can find.
Right. So if you have like 10 of Z and 0, you have 10 equations.
Yes. No, that's not 10 equations. That's a sequence of 10 numbers. Each of these things is not an equation. So if I have 10 of those things, if I have 10 perturbative guys,
yes,
then what I have is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I am approximating the exact result with some error. And so let's say that if you reach this point, and now I'm making up numbers, I don't know the numbers by heart, but let's imagine that what you get here is not square root of 2, but it's a number which approximates square root of 2 with, say, I don't know, I'm making up numbers, with 10% error. And then if you have more data, then the error in which you approximate square root of 2 is going to be less and less and less. So you just have a sequence, you don't have equations. Right? This is a large order relation. tells you how this sequence should behave. All right. Now let me be slightly more schematic, telling you how all these things generalize to the nonlinear case. Because basically the formula are all the same. I just have to take into account the fact that there are many instances.
Also, somehow this model was just an integral. It's not one.
This was the simplest possible toy example at the front.
But can you do something here?
We can do string theory. I'll show you at the workshop.
But you do.
Field theory is harder because of
Or
normalization.
one-dimensional quantum mechanics.
Quantum mechanics, no problem. In fact, quantum mechanics, much of this starts with quantum mechanics.
So in that case, you really have this was not an instant time, so just a stationary point.
Yeah, I mean, the language, again, like Frank was asking the other day, sometimes you have to have renormal bonds, sometimes you have to have deep rings.
So I'm not sure if you discussed the case of instant times or not.
So tomorrow at the workshop, I will tell you results in string theory and matrix models. That's tomorrow or after tomorrow.
But maybe just a big question then instant times, if there is sometimes that and instant times.
Yes.
And you do both.
In quantum mechanics, yes.
That's usually very important. You have a systematic way.
Yeah.
Because that, from here it was clear how you do instant time, V. But it's not V.
I'll show you some other formulas.
We had instant times. That's not also correct.
In fact, at the workshop, I'll show some formulas for stuff that we don't know. We call them generalized instantaneous. We don't actually have a physical interpretation of what they are yet. So we don't know how to describe them to my classical. Even though we know they must be there because they come out of this class.
See them.
Yes, we can see. All right. So what if I want to look at the nonlinear problem instead? And let's stay within this realm of the integral that I raised before. And let's ask, what if I was interested not in computing the partition function, but the free energy? And you tell me, oh, come on, you already compute the partition function, just take the log. Yeah, I know all that, but again, we want to illustrate in a simple toy model how these things work. So what's going to happen is, because I knew the differential equation for z, I can write down the differential equation for f. Let me write it for you. And now, this equation is nonlinear. Here's a nonlinear piece. Everything else is very much reminiscent of the equation for z. And what this guy is basically telling you is that if I assume that there's only one instanton sector, then there must be 2, and then there must be 3, and then there must be 4, and so on. Right? So what we're going to have to do this calculation is we're going to be, and basically what I'm going to tell you now is generic for any nonlinear equation we give. I will show you later also at the workshop how to do this for Ponivet type equations that describe non-critical string theories. But they're harder than this because somehow there is no linear problem associated, not in an easy way. Right? But in this case, let's see, what could we do? Here's a couple of steps that you can do just schematically with some results to get some minor check. The first thing is I could go and look at the perturbative set. And then if I'm just going perturbative, I plug in an ansatz that looks like this. So just a standard perturbative summation over x. And it's not too hard to see that if you use this into this differential equation, you're basically going to get a recursive equation out, which is going, let me not write it for you, but it's going to tell you how the fn plus 1 guy is computed out of the earlier. And while for the partition function this was exactly solvable, and I showed you what the result is, it was the 4n factorial divided by 2 to the 6n times 2n factorial times n factorial, with the 2/3 again exponential term that we saw last time. And here we have to just plug this in the computer and recursively generate data. So we're in a case Like you're asking, well, what we have only is those dots. So we have sequences, and we have a lot of sequences. And if you do this calculation, then you can use yellow tricks up there. And what you can do in yellow is to check numerically, just plug it into a computer. And you check that this sequence behaves like this. Exactly as you would expect it at living order. Plus some living stuff, let me not start computing the sub-living stuff. And numerically you can see that A is to a very good approximation 3/2. It should not be a surprise, we already computed A exactly before, and the log should kill the transseries. And this Stokes combination is to a very good numerical degree, I times square root of 2. So you say, okay, my perturbative data is telling me that they're not enough. They need non-perturbative gas. So let's add in some non-perturbative gas. So then I'm going to augment my initial gas and go non-perturbative. And the first thing that I'm going to do is I'm going to consider a generic non-perturbative cycle. So instead of just writing here a perturbative ansatz, I'm going to include an exponential term, right? So just like we've seen last time. So now the non-perturbative contributions could be schematically of this form. There's the instantaneous action. There are some characteristic exponent that may appear. We already discussed that last time as well. And here, oh sorry, there's a sum. And here is a power series of the L instantaneous. And I grab these ansatz and I plug into the differential equation. And then I start getting lots of recursive relations at lots of different orders. The first thing I get is the following. So this is at leading order. A is equal to 0 or 3/2. And beta is equal to 0. Then I start doing it at next order. I'm going to start seeing back that recursion. Then I keep going and I start seeing basically recursions of this type. Where here I have lower perturbative guys. Schematically I'm writing them like this. And here I have lower instantaneous guys and lower order. And so I have, this is an analytic. I can compute recursive equations that tell me everything about A, beta, and all these coefficients. And then basically what all these people are going to be doing is constructing for me the transseries. Of course, I'm always putting this in the computer and waiting and so on, that the computer gives me some data, and it's going to be producing me non-exact data, right? This is a non-linear problem. Let's imagine that I didn't know how to solve it. So I don't know the exact solution. And in fact, for most of these non-linear problems that we're going to find in, serious problems, not time models, we're going beyond the classical elementary function. So basically, we're defining new functions. So these objects are defined. If you want to compute the partition function of the quartic matrix model, you can compute that, and that's a power series of theta functions. So it's not simple elementary function.
This kind of position you can't apply generally, right? You don't have a differential equation for most of the stuff.
Right, so again,
what you will usually have is only the perturbative series. Can you say what will you do if you only have the perturbative series?
yeah, okay, so let me tell you two things. The first is that I'm doing again time models, but it's not the case that generically you don't have equations. So if you wanted to do non-critical strings, they're all defined by Olivet type differential equations. So you can do a lot of stuff there. If you want to do matrix models, you can always write down finite difference equations for the recursive coefficients in your orthogonal polynomials. So from there you can compute partition functions. So basically you have another large class of things that you can do, because what I'm saying is by no means restricted to differential equations. This applies to finite difference equations, it applies to integration, very likely applies to functional integration, so you have a lot of things. If you want to do harder string theories, for instance, if you want to solve generic topological string theory, then you have recursive relations, the Hallmark canonical equations that are going to be computing for you the Chin's expansion. It turns out that these methods also work for the Hallmark canonical equations. I'll talk about that at the workshop. So I mean, there's large classes of problems which are by no means restricted to a simple differential equation in which these things work. So what I'm showing you is again the simplest possible time model to understand the basics. Now, if you only were to have the perturbative data and nothing else, because that's all the machine that somehow you got produced for you, you're restricted to doing this. You will always be restricted to finding numerical approximations to your instanton action, to your non-perturbative 1 instanton, 15 instanton contributions, which might have some errors because your data may be limited. But, you know, generically, so the first paper we ever wrote on this business, we did, I don't know, Hurwitz theory with 10 terms. And we got the correct result with an error of order 11%, which was not that bad if you only have 9 terms, right? But, so you can have fairly good approximations even if you don't have a lot of data. And then the challenge is to explain by other means those values which you already know approximately. But if you have more stuff, then you can get more mileage out. All right? So we play this game, and everything goes on in the way that you expected. So now what have I known? I found out that I have to include an instanton action 0. I have to include an instanton action 3/2. I have recursive methods to compute all these coefficients. So what I would generically should be writing should be a transseries for the solution of that problem. Let me write down what is the transseries for the free energy of this toy quartic integral. And then we'll see that that transseries, well, I will motivate, I will not show, that that transseries enjoys the same properties that the linear problem enjoys. Okay? And I'll write down for you a couple of general formulae. So, if I have all those people above there, what I should actually be considering as a general solution should be a transseries. So now I have to include a transseries parameter, sigma, which should look like this. So the transseries parameter is appearing there. And then all I have is the exponential terms that are there already in pink. Where all those phi's are asymptotic series. Alright? And now what happens is that the results we had for the linear case generalize. Now they generalize in a slightly contrived way. I'm not going to give all details. You find them on the Borel plane because of this multitude of instantons. Basically, if you want to be more precise, because of this term there, somehow the argument of the exponential is telling you about the location of singularities on the Borel plane, so you can define a projection. So let's imagine that that A was along some direction theta. I'm going to have singularities along the ray. And now if I want to define an alien derivative in some way, certainly, we already discussed that maybe last time, the average of the plus and the minus is not going to be enough because it's missing a lot of information. As we discussed last time, it's missing, for instance, information about that contour. So somehow I need to devise a way in which I include everybody at the same time, and that's how this alien derivative is going to appear. It's going to be, I'm just going to write it in words, an adequate average of all possible resummations. So basically of all possible blue contours in that picture. And you'd say, why would you want to do that? And the reason is the one that I had written before, because this is the only way in which these objects will satisfy the Leibniz rule and will be a derivative. Otherwise, it's not going to be a derivative. Of course, you could say, I'm happy to live, and some people actually work with it, I'm happy to live with just something which is not a derivative. Sure, that's if you want to do it, please go ahead. You just are not going to get as much mileage as fast as you do if you work with it. Yeah.
Why is this the relevance? You think that this is a derivative has nice property, but so there is a function which is deterministic, which when you take across this line, it jumps by a certain thing.
Yes.
Now, I think looks like when you jump from across this line to this line, cutting all of these, it should just add up the contribution of everything. Why is it this average, the adequate average thing that you are defining and not just the simple thing?
It's just the way that it sort of works out. Let me give you the results, and then we can go back to your question. So the first thing is that I'm just going to be schematic. So if you choose to work with the alien derivative, what you're going to get is the following. So let me write here parallel. So this is alien derivative. And this is Borel structure, Borel singularities. And I'm just going to make a case of things why they look the same. And this is going to be based also on what we've already seen last time for the partition function. So the alien derivative is going to look like something like this. It's going to be the delta operator. It's going to be non-zero at all possible singularities, and only there. So it's just at all the pink crosses. And if you apply it to the nth sector, you're going to get back the following. So you get back a Stokes constant, and then you can get back a numerical factor that appears times phi n plus k. I'll make a drawing of what this implies. The k's are not arbitrary, so it turns out that you need to have k less or equal to 1 and different. Okay, so bear with me for a second. Now, if I was to look at Borel singularities, let me just make sure that I use the same notation. The Borel would work in the following way. We'll make some plots of this to make things clear. I'm looking at the Borel of the nth sector, and it's going to have singularities close to all the pink dots. So it's going to be singular around S equals k times A. And this is going to be given. So if you remember from the partition function, there's usually a pole, and the pole is associated to the constant term in the power series. So it's always there. Let's not worry about that. Let's just look at the logs. It's enough. And the structure is basically, as you'd expect, there's the logs. S minus k divided by 2 pi I. And what's in front here is a coefficient. It's not the Stokes coefficient, it's the Borel residue. It takes you from nth position to nth plus k position. And then here is the Borel of phi n plus k, evaluated at S minus kappa plus k. And now the only constraint is that k is non-zero. These coefficients, they're all related to each other. So I'm not going to write formula for you, but there's formula that tell you how to go from Borel beta to Stokes beta and back. Okay? It's not so hard to see. There's of course also plus homomorphic terms that could be here that I'm not taking into consideration. And you can see that basically this adequate average of all possible resummations is what's going to allow you to extract away the Borels and obtain a formula that looks like that, just like we did for the partition previously, in such a way that this satisfies the Leibniz rule. Alright? Now, what can I do with this? I can try to understand this pictorially, what's going on. Let me see now. Go to the next one. So what's going on here is the following. Let me just do the plot and then we discuss all the formulas together, okay?
This pink dot that you have,
Yes.
these are all supposed to be these logarithms like that.
That's why I want to make another plot. So let's just have everything, the information on the blackboard, and then we review everything that I'm doing, because this is slightly tricky. If we go just step by step, you don't get the whole picture. So I prefer to first put the whole picture on the blackboard, and then, even if it's right now slightly clear, and then we understand exactly what's going on. What are these formulas telling us, and how do those formulas translate to the picture I have on the Borel plane? So I can do the following pictorial representation of the transseries which is up there. So I'm going to write the transseries basically as a chain, where in each node of the chain I'm placing an asymptotic power series. That's the perturbative guy. This is the 1 instanton, the 2 instantons, 3 instantons, and so on. So what's happening here is that what are the alien derivatives doing? They are implying motions that I can have on this chain. This chain is my transseries, and this constraint here is telling me that I only have one way to move forward on the chain. So I can jump by 1. That's delta of plus A. The plus A is a sub plus A. And this is always the same thing, no matter where I start and I end. So here, I can also move forward just by 1 step. That's delta plus A. And here, the same thing, delta plus A. And so on. Okay? This tells me that sort of forward motions are particularly simple, because if I want to go from phi 0 to phi 3, I just have to iterate delta plus A 3 times. And this is why the relation that I wrote before for the large order is very simple when I'm just looking at people who are ahead of me. So when I'm looking at what's going on along the ray. But that's not the complete information of what's going on. For the perturbative, I can't go back. So I don't usually care about anything else. But if you start asking, what if I try to play the same game that I played for the perturbative at a fixed instanton level, then the large order relation is not only going to tell me about singularities ahead, but it's going to tell me about singularities behind. And those are extremely hard, because those are now associated to a lot of possible different motions that I can have, because I can go back just with 1 step, or I can go back with 2 steps, or I can go back with 4 steps, or whatever. Because all k's less or equal than 1 are allowed, and this means, so here this is for instance delta minus 2a is non-zero, and so on. And so this is going to tell me that when I'm evaluating Stokes automorphisms, which are, remember, the exponential of the sum over, just, well, there's another exponential here, over the singularities. When I'm doing this evaluation for the instanton sectors, this evaluation is much more tricky. Okay? Nonetheless, it can be done. So again, let's just review everything we have here on the blackboard. So I started with a nonlinear differential equation. And I plug in a perturbative ansatz, which told me, wait, that's not enough. We need more people. And then in the blackboard that I just erased, we said, okay, let's try to do a transseries ansatz. And the transseries ansatz tells me that I can write down a transseries like the one above, with no big deal. If I want to understand it in the same way that I understood the partition function, so what I'm trying to say is that all formula apply. All formula apply with their adequate generalization. And this is a generalization. If you want, the perturbative case was particularly simple because I can also make a plot for the perturbative transseries, and the perturbative transseries was just this. It's a sort of a finite chain because there's nobody else. And I had a forward motion that was delta of plus A, and I had a backward motion that was delta of minus A, and I had nothing else. So this is the natural generalization, with the caveat that because I am choosing the definition of that delta such that it's a derivative, I only have one forward motion and many backward motions. And, just to finish this, while the forward motions are of the same type of what happened for the linear case, the backward motions have this funny property. If I compute the commutator of two backward motions, and this should not be very hard to guess, given that we're doing a one-dimensional chain, looks like this. So it's resurgent. And now that's one of the things why it's good that this object behaves as a derivative. It's because it's going to have nice properties of this. Finally, one last, let's see. I should be stopping soon, or?
You can keep going for a few more minutes for me.
Let me not overdo it. So, yeah, I'll be showing lots of plots at the workshop, so let me just give you one more interesting reason why this should be a derivative, given that, you know, that was the main question that you guys seem to have, is that this can be further improved in the sense that if I write down that relation for the full transseries, not just for its sectors, that relation can be written in the following way. Exponential of minus omega over x times delta omega. It takes the exponential for the full transseries on f, that's the transseries above, is a Stokes function of sigma, which is just a power series expansion of all the coefficients I found, times and this is known in this business as the bridge equation. Because as you can tell, it's making you a bridge between alien derivatives and standard derivatives. Only that the standard derivatives are acting on the moduli space of solutions, because they're derivatives against the transseries parameters. Now, if I were not to choose delta to satisfy the Leibniz rule, I would not arrive at such a powerful formula. So again, you can't decide to not do so and to just consider simple glue averages, but you're going to lose a lot of information, or at least a lot of adequate tools that can bring you much speed on knowing many more things. All right, so I'm not sure if there's this questions on this. I mean, this was a little bit vaguer than the linear case, but I think the linear case was well beaten to death, so I think it sort of motivates why the non-linear case should be very simple. And at the workshop, then I will tell you how to apply this for lots of cool examples in string. Any questions? Yeah.
It seems that the equation seems to provide a systematic way of defining the alien derivative.
That's true. In fact, the way the story goes is that you start here and you end up there. So the reason why I did it the opposite way from what's usually done is because it's much simpler to motivate the linear case with just looking at Borel transforms and the singularities and then reach the endpoint. If I would have started the lectures here, nobody would have listened after 10 minutes. More questions?
Any other questions? Okay, let's thank you.